have a V on it.
Okay, we're going to start talking about commercial gutter flaws. And as roadway designers, I assume that you guys need to do this. How many of you have done it before? Analyzing gutter flow. Our learning objectives are going to be to list the variables that affect flow in gutters. We're going to demonstrate some advantages and disadvantages of composite gutter sections. We're going to apply the gutter flow ratio concept, and we're going to calculate the flow capacity of a gutter section, actually gutter sections, because we're going to do uniform slope and composite slopes. So, water on pavement can do a lot of things, and none of them are good. You can interrupt traffic because if you're in not only on a high volume road, but even a lower volume road, but mostly in high volume, traffic slows down when you have a lot of water. Right? That oil and grease that's on the road, that'll come up to the surface when the water hits the road, and that'll reduce your skid resistance. It can increase your potential for hydroplaning because you can start hydroplaning at about 45 miles an hour. And of course, nobody likes to be out there when it's really heavily, especially when you go past trucks and all that spray comes up. You can't see where you're going. That happened to me. I don't know where it was. It was in North Carolina. I was going past a truck. Literally, the truck was double. You have a trailer behind the trailer. It was bad for about 2 seconds. We were just like, oh, we're going straight. So, yeah, all of that is just bad. So what you want to do is get that water off the road. So when you're looking at getting it off the road, these are some things you have to consider. Surface drainage, and by that we mean the spread, really. Do you know what spread is?
No.
No? So, yeah, it's how much you're going to allow the water in the gutter to spread out. Are you going to let it go into one of the travel lanes, or are you going to keep it to the shoulder in the gutter? So that's your spread. And that's going to define a lot of your design. It depends on the classification of the road. So higher volume roads like interstates or major roads probably don't allow any water, and I'm going to show you that. You don't allow any water in that travel lane. And I think, well, we'll see in that in a minute. So you also need to know what that gutter flow is and what your inlet capacity is. Can the inlet handle that gutter flow? And if it can't, how much bypass flow are you going to have? That bypass flow, if it doesn't get into this inlet, it's going down to the next one. So you're going to have to add that bypass flow to your calculation of what the discharges in the gutter going to the next inlet. So, and we don't get into this too much, but when you're doing trying to figure out what your flow is, at least for the first one, you're probably going to use the rational method. And what you do is look at your travel lane. And if it's just a 2-lane road, you usually have a crown in the middle of the road, and so each side is going down a cross slope of 2%. So you're only looking at that one lane that's draining over to your gutter, and then it's length before you get your inlet. So that's how you figure out your area. Okay? And that will determine your time of concentration and your intensity, and you can figure it out for the first one. So it's a little bit different as you go along. So when you're talking about pavement drainage, these are things you have to look at. You've got to know what your storm frequency is, and that should be in your EPG. And it tells you what storm you're going to design for. It's usually 10-year for minor roads, and it could be a 50-year if you're in static. And we'll see that a little bit too. You also need to know what that allowable spread is, and like Dorothy said, she was saying it's going into half of your travel lane, but your EPG has specifics there. So classification of the highway, like I was saying, is it an interstate? Is it heavily traveled road? Is it 4 lanes wide? Is it that gives you an indication that it's heavily traveled. Is it out in the country, minor collector, just a minor road, things like that. Your design speed, you need to know that. Is it over 45 miles an hour or is it under 45 miles an hour? Projected traffic volumes, mostly because of cost. If you think this road is going to be, well, it's probably in the planning process, but they might be widening the road for projected travel, and you're taking that into account when you're looking at how much spread you're going to allow. Intensity of those rainfall events, we kind of talked about that before. In arid parts of the country, like in the Southwest, they might be allowing a 25-year storm because they don't have that much traffic in some areas. It's a flash flood and then it goes away. It's just stuff like that, different variables for different states. So you're looking at your capital costs. If you're not allowing a lot of spread, that means in a high event or a low frequency storm, say a 25 or 50-year storm, your inlets might be spaced very close because you're trying to account for that spread. You can't let it go too far out, so you have to put your inlets closer and closer. And just other considerations. So here's your Missouri design frequency, and you can see for a major road, the typical is a 10-year frequency. That non-typical can look like that referred to if you're on a super elevation. I can't remember what else it was. There are a few others they name in your EPG. But if it's a critical area like a sag, then you're designing for that 50-year. And in a minor, again, it's pretty much the same, except in the sag, you're going for the 25-year. But that non-typical is up to a 25-year. And critical in the sags are at underpasses or at grade intersections where you have a lot of traffic and you don't want that flow to get out into the intersection because then you got spray going everywhere because cars just keep coming through. So whenever you're at a critical intersection or most intersections where there's a fair amount of traffic, you want to try and collect that water before it gets into the intersection. And here's your design spread. So for interstate, it's up to the shoulder width with a 12-foot max. And if it's greater than 45 miles per hour, it's up to the shoulder and or parking lane with a 12-foot max. I think that's what Dorothy might have been talking about.
I know, well, we're designing a mix of their it's not like super heavy.
Okay, so it might be somewhere in here too.
Yeah.
Okay. So you can see them all. Minor ones less than 45 miles per hour, you can do a shoulder plus half the lane. And the lane is usually about 12 feet. So half a lane would give you 6 feet. And a minimum of 8 feet unflooded when you have single lanes. So hydroplaning. See something. I just wanted to tell you what hydroplaning is. It occurs when the drainage capacity of the tire tread pattern and the pavement surface is exceeded. So as the water builds up, it produces a wedge in front of your tire, and that produces a hydrodynamic force that actually lifts the tire up off the pavement. And that's when you lose steering and you feel like you're just flying down the road because you really are. You're up off the pavement. And that can happen at 55 miles an hour with as little as 0.08 inches of water depth. So it really depends on how good your tires are, how good your tread is the road really smooth? All of these things add up to hydroplaning or not hydroplaning. So it's a function of that depth, the roadway geometries. Is it a really flat road? Has the water been able to get off? Your vehicle speed, and like I said, the tread depth, tire inflation pressure. Why do you think that? Why does your tire inflation have a tire slide? Exactly. So more surface area, easier to lift you. And condition of that pavement surface. That's why a lot of times out there you'll see grooved pavements because they're trying to prevent hydroplaning because it gives a place for the water to go. So AASHTO says that really hydroplaning is a condition analogous to snow or ice on the road, and it is up to the driver to manage that. So you're expected to slow down and realize what's going on and not hydroplane. That's what they're saying. So two main factors that are influencing the spread are the longitudinal slope of the road and the transverse slope, that cross slope from the middle of the crown of the road to the gutter. So you should have grades of at least 0.5%. We never wanted to get less than that because you want the water just to move. You want it to go somewhere. In special cases, you can be 0.3% or 0.2%. We prefer not to see that. If you're in a really flat area, you want a rolling grade. Has anybody ever done that? You know what I'm talking about? So you, instead of just having a flat road, you actually build the road up a little bit and bring it down. Build it up, bring it down. That gives the water some place to go and get off the road. So that's a good thing to do. I've seen it in some southern states, but not everybody's aware of doing it. In the sag, underneath those underpasses, you want a minimum slope of 0.3% within 50 feet of that sag. And the reason is you want to have some kind of slope to get that water to the inlet. So if it's less than that, water doesn't move too fast. So give it at least a minimum of 0.3, but 0.5% is better. So to check to see if you are meeting that 0.3% or what you are meeting, you want to calculate this vertical curve constant. And let me just, and that is saying it's the length divided by these grades. So what we're talking about here, this is your length this way, and then your grade 1 and grade 2. So this grade is coming down, this grade is going up. And so if you use that, and your K is equal or less than 167, then you have met the requirement of the minimum grade. Okay? So be careful of the signs too, because that G1 is actually minus a minus. So cross slopes can vary from 1.5% to 6%. Typically, you'll see 2% used out there. And you can increase that cross slope for really wide pavements. So if you have a major road out there, maybe it has 3 or 4 lanes, what you do is near the median or the inside lanes, those first 2 are graded at 2% slope. And then at the 3rd and 4th lanes, you can add 0.5 to 1% of slope to each of those, up to a maximum of 4%. And the reason you're doing that is because 4 lanes of traffic, that's 48 feet of traffic width, right? And this water has to come across 48 feet. By the time you get to that 4th lane with only a 2% slope, that water is building up. So if you increase the slope as you're going out, the water's moving faster off the road, so you don't develop such a high depth in the 3rd and 4th lanes. You don't want to go above 4% so much because drivers will notice that. And it makes them uncomfortable, and especially in a rainstorm, they'll slow down even more. So here's a typical gutter section, and what you can see, kinda, is that the gutter section is at a steeper slope than the cross slope of the road. And its gutters can be anywhere from about 12 to 39 inches wide, typically. So this is a triangular, gutters are typically a triangular cross section. So T is your top lift. I think Eric talked about that yesterday. Whenever you see T, that means top lift. SX is the cross slope of the road, and this S, or it could be SL, is longitudinal slope of the road. And here are some typical gutter sections. So the one on the left is the uniform section, and it's just the cross slope of the road continues until you hit the curb. And it's, like I said, it's usually 2%. And then we can have a composite cross section. So it'll come to, within the gutter, that's 2%, and then it will increase to something else. And so when you want to figure out calculate the flows and what's happening in each section on the street and in the gutter, you can divide it up into sections. And this A, you're going to be seeing this later on, that A is the difference between if you extended this 2% slope to your curb and the difference of this steeper slope here. So that is what your A is. In Tech 22, it doesn't really tell you what it is. So there was some confusion there for a while on my part. So here's the uniform cross slope. If you want to find where the depth of the curve is, all you have to do is multiply the top width, your allowable top width, times your cross slope, and that will give you the depth. And if you want to find out what your Q is, you can use this modified Manning's equation. And the reason it has been modified is that your top width can at times be 40 times the depth of the water. And the Manning's equation really doesn't accurately reflect that difference in top width to depth. So they modified it. And you'll notice here this K sub U is not 1.49 anymore, it's 0.56. And I'm going to be showing you a number of equations, and those KUs keep changing. So pay attention, it's not always the same. Make sure you know what it is.
What is S sub L?
S sub L is the longitudinal slope of the road. And so, this isn't a very hard one. You'll be given the SX, you kind of know the SL, you know what your allowable T is, you know K sub U, and you can figure out what N is from the material your road is made of. Is it concrete, is it asphalt? There are N numbers out there for that. So velocity for uniform slope, you can use the continuity equation here. We're showing that, and we're giving you the equation for the area, which is the top width squared times the cross slope divided by 2. Or you can actually do a velocity computation using another modified Manning's equation, and notice the K sub U now at 1.11. So you can do it either way. It's just, I'm sorry, this L should not be capitalized, it's a little L. And here's the composite cross slope. So again, you could use continuity, B equals Q over A, or if you want to find the area of composite cross slope, it's just this little equation, no problem, right? So what this is saying is, did we just show that before? It's kind of the same thing as this. You're saying the top width squared times the cross slope divided by 2. And now we're saying for this composite section, it's just SW instead of SX times the width, W, that W up there, squared divided by 2. So that is giving you the area here, or here, I should say, in this area. And then the rest of it is just SX times the TS, and then it's TS over 2 plus W. If you really sat down and thought about it, you'll figure out that it all makes sense. So we also need to know about gutter and frontal flow ratio. So what is that? The E sub O is the gutter flow ratio to the frontal flow ratio. The gutter to frontal flow ratio. is that what it is? Gutter flow ratio is the ratio of flow in any unique width to the total flow. Sorry. So, whatever this width is the flow in that width to the total flow. That's your gutter flow ratio. So, I think in your book, this heading is wrong. It should be this one. Does it say the same thing as the other one?
Yeah.
Yeah, that's what I thought. I saw that. So, yeah, it's the gutter to permaflow ratio for a uniform cross slope. And this is how you find it. So it's just 1 minus W over T. So it's to the 2.67. So it's a gutter to permaflow ratio. And here it is for the composite cross slope. You look at that and your eyes kind of cross, right? It's not that it's so hard to do, but it's just like that. So,
Keeping track would be a little bit difficult.
yeah, a little bit, and just working on the calculator and stuff. So, we have this. Yeah. So isn't that better? So, all you do, you have to know what your W over T is, and that's pretty easy. You know your gutter width, you know what your allowable spread is. So you come in and you go up to the line that reflects your SW over SX, because it's a uniform slope, that's going to be 1, right? Because they'll both be at 2% or whatever your cross slope is. So you go up and then you just go across and you find out that your E sub O, or gutter to permaflow ratio, is 0.53. That's a lot easier than using that other thing, right? If it's if you have a composite slope, in this case, what do we use? Actually, I'm supposed to let you use this. So if we said that SW was 10% and SX is 2%, what would your SW over SX equal? Yeah. So in that case, your WT hasn't changed. You come up to that 5 and you just estimate where the curve for the 5 is, and you come across and find the 0.73. So what this is saying is that in a uniform cross slope, 50% of the flow is in about 25% of the width. Because your W over T is 2 over 8, that's 0.25. So if you come back here, your W over T was 0.25, and you come across and a little more than 50% of the flow is within that 25% width. And in the composite section that we showed, it's saying that 73% of the flow is in 25% of the width. And that's one of the reasons you might want to use a composite cross slope, because your gutter can handle more flow, and it's going to be a little more efficient. So for composite gutter analysis, your discharge is equal to the discharge in the street, which is this area outside the gutter, divided by 1 minus that E sub O, or your gutter flow ratio. So it's actually a little easier to figure out than you might suspect. And we'll show that in a little bit. So flow in vertical curves, or sags, the grade becomes flatter and the speed limits still apply. But your inlet spacing will get closer. A lot of times when you have an inlet in a sag, you'll also have flanking openings, inlets. Because if a lot of times, most of the time in a sag, you'll have a combination inlet, and it will be a grate and a curb opening. But that grate can get clogged, and sometimes so can your curb opening. Not a lot, but curb openings are pretty good with debris, but they can get clogged. And if that happens, as the water rises, then it'll go into these flanking inlets. And that gives you extra protection because most of the time those sags are, I don't know, if you see major floods, and I see it in Denver quite a bit, or I used to, they started fixing it. These cars would be trying to go through 4 feet of water. You know, it's just like, and it was an important road, so that's why they're trying to do it. Not good. That was it, so we just went through that. So, we do have a workshop, surprise, surprise. So let's look at that. We'll just go ahead and do it because we're running just a little bit behind. Let's do that. So let's just read it. You're going to do a uniform cross slope. Well, actually, I should ask you, do you have any questions first? No? Yeah.
So once we get the queue now here, we need to design the gutter itself, like find the sizing, the gutter, right? The width and the height. Like from that queue, we can use it to figure out what's the size of the gutter.
Typically, your curb height is going to be about half a foot or 6 inches.
So
That's
we're looking
typical.
just for the length of the gutter.
Yeah.
That's all this is, right?
Yeah, and you, for the width, or the width
Oh,
of the
the
gutter?
width of the gutter,
Yeah, that's probably a standard in the state. You probably have a standard I would use, and I imagine it's about 2 feet, but I don't know. You'd have
So
to-
it's kind of checking if that if we need more than one gutter. Like if we need one or two besides each other.
Oh, you're not the gutter, you're in the inlet.
Gutter
Yeah, we're going to talk about inlets in a minute. What you want to do is, we're going to talk about inlets in a minute. So what you're really doing here is finding what the capacity is of your gutter. We're just talking about gutters right now, so not so much the inlets. So you're ahead of me. Any other questions?